so the so you guys are, some of you are Monday, Wednesday, some of you are Tuesday, Thursday. Have you guys gone over both type of reactions? Or have you guys just gotten to E2? We've gone over both. We're done with E1. All right, so it's cool. So you guys know with E1, the key to E1 stereochemistry is irrelevant, just like with SN1. The key with E1 is that rearrangements can occur, and you're going to be creating a double bond that is most stable as possible. When it comes to stability, it comes to how conjugated or how substituted it is. I guess the substituted would be the better word. And you guys remember my statement last week, right? So this is more conjugated than this, and this is more conjugated than that, and this is the most conjugated that you can get. All right, so do you guys see that? So both coming off of the double bond, it comes down to how many carbon groups are bonded to the double bond. The more it is, the more conjugated, thus the more stable. Also, a trans is more stable than a cis, even though they have the same number of carbon groups coming off of it. All right. So somebody struggling to get in.
And then the one on the top left is more stable than the trans and the cis. That one with the arrow pointing to it.
It comes down to relativity, and I'll show you guys an example that touches on this as well. But the general concept that you guys need to apply is the more stable, the better for E1, and in order to create a more stable one, the more conjugated it has to be. For E2, the key statement is this, all right? So you guys know this statement, right? You guys have heard it. If Jermaine hasn't mentioned it, maybe Chris has. You guys have to know that the leaving group, if it is, say, dashed, you guys have to take a hydrogen from a beta carbon that is wedged. The technical term that they use in anti-coplanar, but we just say trans. And we will go over an example of that. If he hasn't gone over it in SI yet, here's your table. Have you guys seen this table before? No. Okay. Well, it's your new pride and glory. All right. So you guys can kind of forget about your SN1 and SN2 table, because this now takes care of both chapter 6 and chapter 7 reactions. All right. So here you have your substrate and leaving group, if it's primary, secondary, tertiary. And remember, we determined strong, weak for SN1 and SN2. You're doing the same thing for E1 and E2, but there's just something else you have to consider, nucleophile and basicity, and that this table helps you determine. All right, so your classification of your nucleophile and base, you determine from this table here in order to piece everything together. All right, and we will go over that rationale. There's a notification I have up here. What was it? Guess not. All right. So that's naming to jump into reactions. All right, this is primary, secondary, tertiary.
Primary.
Primary, and remember this because I'm gonna because I'm gonna scroll back up. This ETO negative. All right, what category does that fall into?
Strong base.
So you're saying strong, but strong,
Strong nucleophile. Strong.
strong. All right, so it's going to be strong. So primary, strong puts you at an SN2. All right, so you're simply just going to have a simple nucleophilic substitution. So we're just going to replace Br with the nucleophile. All right. This TBUO, do you guys know what that is?
Tert butoxide.
Yes, tert butyls. That's your big base, all right? So, yep, it is big, and that's when you have to consider your Hoffman and Zaitsev rule. If you have a big base, it takes up a lot of space, right? So it needs space in order for it to take a hydrogen. If one of your beta carbons is more substituted, then there's not much space for something big to come in, right? So the less substituted a beta position is, that's where the base is going to go, right? So with this example, is here in blue or in red less substituted?
Red is less.
Yep. So that's that, right? So that's your preference when it comes to your big bases, all right? So E1 and E2 aside, big bases will prefer a beta carbon that is less substituted, right? So with this one is tertiary. That MEO negative charge falls under what category?
Strong.
Strong. All right, so tertiary, strong leaves you with an elimination reaction, all right? So with tertiary, you have to consider sometimes one thing versus another. Is a bromine a good or bad nucleophile? I mean leaving group.
Good.
Good, why?
Because it has that negative charge. It's a halogen.
Yeah, it's big, right? So big leaving groups will be better to leave. Because, right, that analogy that I used last week, if you're holding a heavy weight and you're holding a lightweight, what are you more likely to let go? The bigger one, right? So hopefully that makes sense. So with this elimination reaction, you're going to be taking a hydrogen, right? So here's your alpha carbon. No, actually, this is our alpha. It's that left, so that's our alpha, right? So you could be taking a hydrogen from beta, 2 or 3. Is there any difference between any of those?
No.
No. So just pick one. Because creating a double bond there, it creates the same exact molecule if it was created here, if it was created here, all right? And we know that with that good leaving group, tertiary, strong, good leaving group, E2, there's no specificity for stability. And in this case, you can't get more stable, right? You're at a tertiary alpha carbon, right? And there's no specificity for a trans hydrogen. So all of these have a trans hydrogen that I can take, right? So there really isn't a difference between making one of these double bonds and making another. Do you guys see that? All right. And this one, it's the same answer. It just wants you to consider the big base, in which the big base wants to take the what? More or less substitute. Big base.
Less substitute?
Yes. All right. So this one is we actually saw from last week. All right, so that chlorine is primary, secondary, tertiary? Secondary. This is a halogen, right? What do we often call halogens? X. Negatively charged halogen will fall into what category? Staring weak. Yep. So secondary, staring weak, is an SN2 reaction. All right. So it's exactly what we saw from last week, right? That I is simply going to replace that leaving Cl. And what happens with the I? It's going to be pointing in an opposite direction, right? Because if the Cl was here, which would be wedged, this SN2 reaction, you guys are going to have to remember that this inversion occurs. So where's that I going to be pointing?
Down?
Down. All right, and extra credit, I actually have a couple questions. So moving along here, I'll draw it out for you guys. So this bromine is primary, secondary, tertiary? Tertiary. Okay. If we don't have a nucleophile base, we just react with the solvent, right? And is this solvent, what category does that fall into? Weak, weak. Tertiary, weak, weak. We're considering this, right? So 25 degrees. Have you guys mentioned, has he talked about temperature yet?
Yes.
All right, so 25 degrees is low. It's about room temperature. Which is low, all right? So with that in mind, we're gonna have an SN1 reaction. All right, so that's Br is simply going to go away, and it's going to be replaced by that Me. Right? And because it's SN1, you're gonna have a mixture of this and the stereochemistry flipped, right? Remember that racemic mixtures for SN1. That's the thing is, in a couple of semesters ago, we started playing around with 50 degrees Celsius. Most often you'll see 25 degrees, which is, in this case, you can almost consider cold. 100 degrees is hot, obviously. Heat, if he says there's heat, that's hot. 50 degrees, you'll definitely have to consider what he says in lecture. Because there's a cutoff, and he may change his mind from semester to semester. So 25 is low. Heat and or 100 degrees is hot. All right, so just be wary of what he says about 50. So that's hexene, that's octane. And here, doing the RMS in my head. All right, so this is primary, secondary, tertiary. Secondary. And we're reacting with a negatively charged halogen. What category does that fall into?
Strong, weak.
All right, so secondary strong weak gives us SN2. All right. So all you would do is simply replace, right? But let's just say it was an elimination reaction. All right. Let's just say it was an E1 reaction. All right. So that Br would leave. So hypothetically, if this was a SN1 reaction, can anybody tell me where they think the double bond would be created with B1 or B2? All right, some people are saying B2. Why? So yeah, not only is the basis small, but the key with E1 is that you want to create a more substituted double bond. That's why, if it were, hypothetically, if this reaction were E1, double bond would be created there. Does that make sense? All right. So a couple former bonding questions. This one, Gen Chem throwback. All right, a low heat of hydrogenation. What does that mean? Does anybody have any clue? No.
Is that like the amount of energy released when you add a hydrogen to the bond? So you're looking for like the less substituted, like they're saying in the chat?
So if you want a low heat of hydrogenation, what that basically means is you're looking for something that is more stable. All right. And what do we know about stability of double bonds?
You want more substituents.
More substituted. All right. So looking at these double bonds, which one is the most substituted? If you just simply break it down, one looks like this. Two looks like this. Three. So yeah, you guys would be correct to say that one is your most substituted and thus has the lowest heat of hydrogenation for that reason. All right. This one. All right, so primary, secondary, tertiary. secondary. All right, is that OH, what category does that fall into, if you guys remember? Strong, strong, yes. So secondary, strong, strong, gives us E2, all right? So E2, here we have beta, beta. All right, does anybody have an idea of where we're going to create a double bond with B1 or B2? And why?
Would it be B1 to get the more substituted double bond?
That's a very educated guess, and that would be correct if it was an E1 reaction. But we're having an E2.
Oh, I see. It has to be anti-coplanar, so I don't think it would be able to be
Yeah.
B1.
What do we know about beta 1? The implied hydrogen is not trans to the leaving group, right? The leaving group is dashed, and the implied hydrogen for beta 1 is dashed. It cannot take that hydrogen, so that's not even an option, thus creating a double bond with B2, because B2 has a hydrogen that is anti, right? So what's our answer? 3, right? But if you guys did determine that it was an E1 reaction, then you guys would be correct to say that you do have the ability to bond with B1 to create a more substituted double bond. And if it was E1, and with that in mind, what would be our answer? So the question was, hypothetically, if it was E1, you would create a double bond with beta 1, right? Because you can take something, yes, it would be 4. That's hypothetically if it was E1. All right, so does that make sense? Question, comment, concern?
That was perfect. Thank you. Can I just ask a question about a previous one? The terbutoxide one you did like a few problems ago. It was in a chair conformation.
Yeah.
Did you
I just
not draw the terbutoxide just because, like, you
no,
know,
you would. There's
okay, cool.
The reaction has nothing to do with the terbutoxide choice, so I just left it alone.
Okay, cool. Thanks.
All right, so this one, the reason I bring it up is because not only is it in bonding, but you may see your options in molecular form, right? And which, don't panic, you just simply redraw, right? So A is actually this, B is this, C is this, all right? So secondary, this ETO, that Na is going to dissolve away because we have a polar solvent. All right, so ethyl negatively charged oxygens. What categories are going to fall into? Yeah, John, strong, strong. All right, so secondary, strong, strong, gives us E2, right? So E2 it doesn't have a specificity for any anti, and we know that if it's E2, we can eliminate C. C is a substitution, right? Is ETOH, is that big or small?
Small?
Small. So this carbon in red versus this carbon in blue, what's less substituted?
The blue?
The blue, but small. The base is small. So it can fit into a space that is more substituted. That's why you're going to create a double bond between alpha and this beta. If it were tert butoxide, B would be our answer because it would not be able to fit in that more substituted space. Does that make sense? You guys see why that's A? All right. This is a rule of thumb I just want to give you guys. If you see H2SO4 or H3PO4 with an alcohol, it's almost always going to be an E1 mechanism. So it's a dehydration reaction, so that alcohol is going to leave and become some water somewhere. You're moving water, so that's why it's called dehydration. And what do we know about E1? What can happen? All right, E1 prefers the most stable, right? This is a secondary alpha. Can it become more stable? Yes, it can undergo a methyl shift just as if it were an SN1 reaction. So one of these methyls can move. And now your new substrate is this, right? Because with E1 you created, now you had the ability to create a more stable carbocation, right? So what's our answer? Okay. Sit tight. Try to solve this one. Because my computer's on 3%. I have to get my charger. So remember that reagent and with an alcohol is an E1. What's going to happen?
The dehydration reaction that we just did?
Yep. And so with E1, you can create something that is more stable if it has the ability to, right? So does that 5-membered ring have the ability to become more stable?
Yes.
How? Yes, Sam, it's a ring expansion. So what happens really is, just to walk through it, I don't know why that's highlighting, but just as if it were SN1, this is going to break and this is going to form, so you get this as your now new substrate. All right, so now the double bond can form. So yes, you guys are seeing that now your answer would be D. And that can happen. It's very often that's going to occur with cyclopropanes, cyclobutanes. That can occur. Like, see, if this were given a ring expansion, it would become, right? It would break. That would form. So, do you guys kind of see how these ring expansions work? All right. And this one, again, these are on the former quiz. So this one, metals, a key point to mention for this one is that, do you guys notice how there's a half arrow with this lithium? So metals like Na, lithium, magnesium, they form radicals, right? You're going to see that in chapter 10. He touches on it, but it's only a half arrow because there's only one electron. We've always used double arrows because when we move a pair of electrons, or we move a double bond or move a triple bond, each one of those bonds is a pair of electrons, right? So if you were to move a pair of electrons onto that carbon, there's going to be a lone pair there, right? And if that's going there with only one electron, you're going to end up with something like that. So this is your answer. This is the intermediate, all right? You guys don't have to know much about that, but so say here, here, you guys remember so metals with an amine, you create a trans double bond. If you have H2 with Lindlards, then you're going to cis. If you have H2 with another metal like nickel, PT, H2 PT, then you go all the way to a symbol. Right. That was touched on a little bit in chapter 4, I believe, but there's your review in case that comes up. So with 4 minutes left, 5 minutes for me because I'll stay a little bit. You guys want me to touch on some naming?
Sure.
Someone feels fine on naming. All right, so let's say this one. This one looks complicated, right? So our longest chain. Remember, we want a double bond to be like on IUPAC or chapter 4, you want your double bond to be on the least number possible, right? So this is actually going to be 1. That's 2, 3, 4, 5, 6, 7. So you have a heptene, all right? And you have a 1 ene. And what is our substituent? A pentyl. So it's going to be simply 2 pentyl, 1 heptene. Right. This one, again, you want your double bond and triple bonds on the least number possible. So let's start numbering. This is 1, 2, and so on. We end up with 7. So I like to break it down. We have a triple bond, which is ine on our first carbon. We have chlorine on our third. We have a double bond on our fourth. Right? And if we were to put that all together, you would get 3 chloro, 4 hept, 4 hept. Ene, again, because you have to say that there's a double bond on the fourth, so hept ene, 1 ine. Right. Something else can come before this, right? We have to designate something. What's that double? What's this double bond? Is that double bond E or Z? Z. Because zame is one way to remember it. Zame, same side. All right, so you would say, where does that double bond occur? On the fourth, so it would be for Z. That's it. All right. So does anybody want me to go over more naming, or are you guys pretty comfortable?
You don't have to do the other one with the triple bond, but I was just wondering if the Z and that ruling also counts for triple bonds.
No, triple bonds, because of the orbitals, are always going to be linear. So the carbons coming off of these triple bonds are going to be in direct line.
Okay.
So
Thank you.
that's why E and Z only occurs. It's only telling you about the double bond. So a couple of people asked me about this file. I, as usual, post the handout in files. But again, if you go to the weekly post that I made to do you guys a favor, because this week is a lot, I commented everything. So let me show you guys. Here's everything. So not only do I walk through how I named the structure, I gave the answer. All right, so here, again, most often I put the answers in red, but in blue, I try to explain how I got there. So primary, strong gives you SN2, primary, weak, SN2, so things like that. So I walk through all the problems that I have on that handout.